All right, so we're going to start talking about waves, and so here's a pretty cool picture of a wave. Waves are pretty cool in general, and so here you just see somebody surfing under a wave, a pretty gigantic wave actually. And this would probably be a pretty dangerous wave actually if they got stuck under it. But anyway, so before we talk about more about waves, we're going to make a connection to what we just learned about. So we learned about oscillations. And so this is kind of an illustration here of how an oscillation is an example of wave motion. So oscillations, they're not waves themselves, but they kind of create waves in the shape of their motion. So if you wanted to create a wave, an oscillating system would be how you kind of created that wave. So here you can see how that path kind of translates into wave motion. Okay? And so something like this could be driving a wave. Okay, and so just a little bit more vocabulary. We're used to using the word period to talk about oscillations. We mentioned frequency a little bit, but frequency is kind of the rate at which waves pass, so the number of waves per second. Wavelength is going to be the distance between, like, the length of one full cycle of a wave, and the amplitude is how much material vibrates as the wave passes through. And there's a couple different kinds of waves, and so for each wave type, we'll kind of review these vocabulary terms. And then another word that's not on here is wave speed. And so wave speed is just, would kind of be the rate at which, kind of like, you could actually measure the speed at which the wave is passing by. Okay, so as we continue though, real quick, frequency. Frequency is something that can be calculated. Okay, if we know how many seconds something oscillates for and how many complete cycles or how many complete waves pass through during that time or how many complete oscillations there are, we can calculate both period and frequency. If we divide cycles by seconds, that gives us the frequency, which is measured in hertz. Or if we divide seconds by cycles, which we've had some experience with, that gives us the period in seconds. So this is the time it takes for one complete cycle to happen, whereas this represents the number of cycles happening every second. So, and this kind of makes sense. If you have a period of 2 seconds, that means that it takes 2 seconds for one wave to pass by something. That would mean that a half a wave passes by in 1 second. And that's why 0.5 hertz for a 2-second period. Okay, so I want you to think for a minute. What does a wave do? When you see a wave traveling towards you, what's moving towards you? I'm going to show you a quick animation of a wave, and then I want you to try to come up with an answer for it. Okay, so here's an animation of a wave. A wave, you can see it traveling this way. What's traveling? What do you see traveling? What's going to the right here? What it turns out is that waves are transporting energy as opposed to matter. So the water waves carry energy, but they're not carrying water. So the water particles kind of stay in place, and when a wave passes them, they move up and down, and then causing the ones next to them to move up and down, and the next ones after that. Okay, there's no actual water moving outward, it's just kind of the particles. And if you were to see a ball sitting on the water, it'd just be kind of bouncing up and down. And the ball might actually start to move towards you a little bit just because of friction with the way the waves are approaching it, but in general it's going to stay in one spot. So here we have an example of 2 waves, and we're going to call these mechanical waves, because a mechanical wave is this vibration traveling from one point to another, and that vibration is transferring energy. Okay, so we have a kind of a pocket of energy that's going to travel to the right. Okay, and there's going to be particles, individual particles, oscillating in different parts of the wave, but the particles themselves aren't moving to the right. Just the energy is moving to the right. Okay, and we have actually 2 kinds of waves. We have transverse waves and longitudinal waves. Okay, transverse wave is where the particles are moving up and down. They're oscillating up and down. In a longitudinal wave, they're oscillating kind of parallel to the direction of the energy is traveling. or I guess the transverse wave we would say perpendicular. So we're going to be focused on transverse waves for now. Okay, and here's an example of a transverse wave. You also saw one in that animation at the beginning. What I want you to try to do though is to pick out individual particles. If you look at those individual particles, you see that each particle is just moving up and down. Okay, wherever you look, you see a particle moving up and down. But the wave itself, you see it moving to the right. Okay, so you have this kind of rightward motion, but really the particles are just moving up and down next to each other. Okay, and so this motion up and down is perpendicular to the path of this wave traveling to the right. Okay, and so this is an example of a transverse wave because this motion here is perpendicular to the path of the energy. So let's go ahead and look at the transverse wave here. We have amplitude, or the height of the wave, the distance away it is from this equilibrium position. So this represents equilibrium right here. This distance away is the amplitude. We call these peaks up here the crests, and we call these low points down here the troughs. Okay, and then the distance between two crests is one wavelength. But another way for defining wavelength is one complete cycle. So from here to there would be a wavelength, from here to there would be a wavelength, and from here to there would be a wavelength. You don't need, when you're measuring a wavelength, it can start from any position, but using crests is just a way that makes it simpler maybe to measure. So let's kind of review some of these terms. If you were to see these three waves pass by you, which one would you say had the highest frequency? This would be this one right here in the middle. Which one would you say has the longest wavelength? Which kind of wave is this? This would be a transverse wave. Okay, the motion of the matter is perpendicular to the motion of the energy. And for this wave, when the wave reaches point X, is point X going to move up, down, left, or right first? We move down first, and then it will go back up, and then it will return to its original position. Okay, as this wave travels, what's transferred from the hand to the wall? It would just be the energy of the wave. The mass of the rope just moves up and down. And finally, which of these waves has the highest frequency and the largest amplitude? It would be wave D right here. Alright, to wrap this video up, I just want to go back to this wave simulation environment here. We're going to be using this to explore some more properties of waves. We have an opportunity here to manually create waves. We have an opportunity to have an oscillating system that continually creates waves. And you have an opportunity to send a pulse. For each of these things, you can change some of the features like the amplitude, okay, the damping, which you can see it damping the wave as it goes. We're not going to spend too much time working on damping. You can also change the tension, which we'll get into. We can add rulers to measure things. We can add a timer to time things. We can add a reference line, which could potentially be useful too. Okay, and we're going to be adjusting some of these factors. You can change frequency, okay, and using them to explore properties of waves.